As we saw before, all simulation at some level or another, when you finally get down to it, comes down to calculating an average of some statistic over a density. And they just differ in what statistics being averaged and over what kind of density. All the different simulators transform problems in different ways to give you different statistics or different densities to be dealing with. But when you do simulation, you're always going to end up having to draw from this density. Because the way you do the simulation to approximate this integral, draw from the population, calculate your statistic for each draw, and average them. Okay? So you're always going to have to be drawing from these densities. And that can, in some cases, be quite obvious how you do it. In other cases, it can be not at all obvious and quite difficult to draw from Fs. And in fact, a lot of simulation is, or the theory of simulation is trying to develop procedures by which you can transform what you're integrating to get an easier density to work with. Okay, because the only hard thing here really is drawing from this density. So what I want to do here now is go through 9 different procedures that for drawing from densities. They are applicable in different situations. They get progressively more complicated. This last one, the metropolis-hastings algorithm, you can do for practically anything. There's only one small limitation on it, but if all else fails, you can always do this procedure. It's a complicated procedure, as you'll see, but you have a fallback. So the idea is to try to find a procedure that's as easy as possible to allow you to draw from your density. Now, I want to say one reason I'm doing this today instead of later is these have no economic content, or very little, if any. They're like tricks of the trade. They're procedures, like computing procedures for taking draws in a computer. And I want to go through all of these today just so you kind of have it, these tools in the back of your mind. And then when we get into the actual economic models, next lecture we're going to start with describing how do people make choices, how do we represent that, so the economics of the situation. We can then draw from these procedures and say, okay, remember this procedure, let's use that. And at that point we'll go into more detail. You'll see the motivation for why we want to do it. But you'll already have in your mind the idea that, what generally it does. So I'm going to go over them kind of quickly today to introduce each of the procedures, and then the practical issues of how to implement them we'll do in the context of when they're being used. So you'll kind of have a motivation for them at that point. Okay, so first, if you've got a density that's simply a standard normal, that is a normal distribution with 0 mean and unit variance, or you have a standard uniform, which is just a uniform density between 0 and 1, equal probability for every value between there. For either of those, the computer codes that you use will have random number generators. So those you just pull them from the random number generator. It's the easiest thing possible. Now, these are actually called pseudo-random number generators because nothing a computer does is truly random. There are a tremendous number of issues involved in how to get a pseudo-random number generator to give out numbers that look random, that have all the properties that you'd want them to have. There's a vast literature on that. There's debate on which programs do the best, all that kind of stuff. Unless you are planning to spend a lot of time investigating these issues and resolving them, it's doubtful that you'll do better than the canned programs give you for their random number generators. So just use a random number generator unless you plan to spend several months on this topic alone. And that's fine. So that's the easiest. Next one is, a lot of times you can just take a transformation of the normal, okay, the standard normal, and get something. For example, if you want something that's normal with a mean of beta and variance of s squared, as you know, you take a draw of a standard normal, eta, multiply it by s, add b, and that gives you your random number that has mean b and variance s squared. If you want something that's a log normal, so if you want a variable that's log normal, you realize that that means that the log of the variable is distributed normal with certain parameters. And so you calculate it simply as the exponential of, take a draw from your standard normal distribution, multiply it by s, add b, and exponentiate the thing. As you can see, if you take the log of this, you're just getting a normal back, which is what a log normal is. So a lot of times you can just do simple transformations like that. Often, however, you can't. Even when you're dealing with a univariate statistic, you cannot simply transform a uniform or a normal in an easy fashion. And then you go to this third technique called the inverse cumulative. In some deep sense, it's a transformation too, but it's a particular kind of transformation. So here, you've got any density F, and it's got an associated cumulative density distribution of capital F. So this is the density, this is the probability that it's below a certain value, it's the cumulative distribution. We note that this is between 0 and 1. It's always between 0 and 1. Okay? And it's invertible because it never goes down. It might be flat in some area, but it never goes down. Okay. So one way to get a draw of epsilon with this cumulative distribution is tells you if you've got a particular epsilon, you read up, and that gives you the probability of having a value of that or less or whatever. Okay. So instead of working that direction, you can work the opposite. You can take a draw from, why didn't anyone correct me here? It's doubtful that it's going to shoot up like that. It goes between 0 and 1. Okay. What you can do is take a draw between 0 and 1 from a standard uniform and then see what epsilon that gives you. So you're essentially working backwards. So the idea here is to draw mu from a standard uniform. I'm always going to use mu for standard uniforms and eta for standard normals. Because this looks like uniform, eta looks like a little n, makes it easy to remember. Okay? We know that there's some epsilon that's going to look like, give you a cumulative probability equal to this uniform that's between 0 and 1. And so we calculate what that is by just taking the inverse of the cumulative distribution. So instead of looking at the cumulative as giving for epsilon, what is the probability of, what is the cumulative probability, instead draw a cumulative probability between 0 and 1 from a uniform distribution and work back to find out what epsilon is associated with that. This works extremely well for things that aren't easy transformations of normals. It is a transformation of a uniform, this particular transformation. For example, extreme value. An extreme value distribution is used in logit models. We'll see it coming up over and over again. And this procedure is a good way for getting draws of an extreme value. The density is E negative epsilon, E negative epsilon, and the cumulative is E negative epsilon. Okay? So what you can do is draw a standard uniform, okay? Recognize that, treat this as if it's a cumulative probability because it's between 0 and 1, and find the value of epsilon that gives you that cumulative. Okay, so we solve for epsilon. So what you're going to do is I just transformed that. It's negative E negative epsilon 1 is equal to log, where this is a natural log. E negative epsilon 1 is equal to the negative of the log. Take a log again. And then take a negative. So that's the transformation you're wanting to do. As long as you can write the f, in theory it's always invertible. You might have problems finding a nice closed form for it, but it's always invertible because there's a one-to-one relationship. So you can always apply this for a univariate density. Now, what happens if we have a truncated density? What if we want to draw from some density, okay, but we only want to draw within a certain range? Okay. So we want to draw within this part of the density, not the whole thing. There are a lot of ways in which this comes up in behavioral models. You can say that the person's going to do a certain thing as long as their errors are between here, but if the unobserved factors fall below this, they're going to do something else, or if they fall above that, they're going to do something else. So these are like cutoff points for your unobserved factors that give rise to a change in behavior. So you're going to end up having truncated distributions all the time. The question is, how do you take a draw from a truncated distribution? Well, we can actually use this inverse cumulative approach to take these truncated draws from truncated distributions by recognizing that we just apply it within this range. Suppose we draw the cumulative distribution up here that's associated with that. Okay. What essentially we're saying is that we want to draw between A and B on this cumulative density. Essentially, we want something. So to get a draw, we just want to make sure that our draw of mu is in this range, and then work backwards to find out what epsilon it gives us. So how do we assure that our mu is in this range? This whole thing goes from 0 to 1, okay? But we want our mu that we choose from the standard uniform to be in this range. How do we do that? Anyone got an idea? Yeah. Exactly. You just rescale the easiest way to do that is draw mu, that's your standard uniform, between 0 and 1, okay? And then create a new mu, an average in a sense, or rescaled value, mu bar, which is equal to an average of these two, okay? A weighted average, 1 minus mu times f of A plus mu f of B. What that's going to give us is a mu that's somewhere in this range. If mu is 0, it's going to give us this point. If mu is 1, it's going to give us that point. And it'll give us anything in between for values in between. So we've now assured that our new mu bar, is in the appropriate range. And then the third thing we do is simply do the inverse cumulative rule again, which is we calculate the value of our draw from that density as the inverse for that. Okay. So essentially we've gotten a mu bar somewhere in the appropriate range, and we read and get our epsilon from that.
What's the drawback of drawing from the uniform from f of A to f of B instead of 0 to 1?
You could do that. You calculate f of A and f of B. That's the same thing. when your computer spits out a random number from a uniform, it'll give it between 0 and 1. And so to transform it to be between here and here, that's essentially what this does. So to take, essentially that's what we're doing. We're drawing between those two limits, recognizing that the computer won't do that for you. You have to do it yourself. Okay? Okay, well this procedure that is based on this inverse cumulative, all the procedures based on this inverse cumulative, with truncated or without, only work when you have a univariate distribution. Why? If you've got 2 or more random terms, there's an infinite number of combinations of those random terms that'll give you the same cumulative probability. So you can't take the inverse. You can't find the unique value of each of the error terms that give you a particular cumulative probability, because an infinite number of them will, or a large number will. And so you can't do this except with a univariate. So now what I want to do is turn to how to handle multivariate distributions, starting with a very important case, but relatively limited. It works for normal distributions extremely well, but not generally. And then turn to what happens as we get more and more general forms of densities on multivariate. So univariate we can do pretty easily. We can always take this inverse cumulative for a non-truncated, or a transformation of mu and then inverse cumulative for the truncated version. So let's now look at how to calculate how to take a draw from a multinomial normal. So suppose epsilon is k by 1, and the density, or let's just put it this way, epsilon is distributed normal b plus omega now, where omega is the variance-covariance matrix, is k by k. We want to get draws from that multinomial distribution. How do we do it? Our computer gives us standardized normals. If we take several of them, we're getting independent draws, but we're wanting draws that are correlated according to this. To do this, we take a Chellis factor. Let's step back a little bit. If we had k equals 1, we already know what to do. If we take eta, standard normal, okay, multiply it by the standard deviation, add the mean, and that gives us the value we want. We already know how to do that. What we're going to do now is a generalization of it, where instead of having just the scalar variance, or standard deviation, we have the equivalent of a matrix standard deviation. That's what the Chellis factor is. A Chellis factor a lower triangular matrix such that lower triangular matrix, let's call it L, that has the property L prime is equal to omega. Okay. You don't need to worry about how to find this L. Computer programs will do it for you. Or you can look up, if you want to program your own thing, you can look up in a standard linear programming, linear algebra text to find out how to do it. But the computer does it. You just have a code say, take the Chellis of omega. Okay. Important to realize that this is also called the generalized square root, okay? Because you've taken this and now found something which multiplied by itself gives you back your original omega. It's also called the generalized standard deviation. The idea is it's a generalization of your one-dimensional standard deviation. Given this, you then can calculate, you take a draw, so the procedure is draw k values from standard normal. Those are eta 1 up to eta k. and call those vector eta. Okay? And then you simply calculate epsilon is equal to b. Okay? So it's got the mean you want times L eta. And now these epsilons have the variance-covariance matrix that you need them to have. First of all, let's verify the properties. First of all, we know that epsilon is normal because we know from the convolution properties of normals that the sum of normals is normal. This is the restriction of this method. You can only use it when you have convenient convolution properties for your densities. You can't use it for just any distribution. But normal has very nice convolution properties. Sum of normals is normal. So we know since each of these is normal, this is normal. We also know that this has beta, or b as its mean, because these are standardized normal. They each have 0 expectation. So the expectation of epsilon is b plus 0. Okay? And we can calculate the variance of epsilon. That's equal to the variance of L eta, which is equal to the expectation of L eta prime, which is equal to the expectation of L eta prime L prime. Okay, keep going. L times the expectation of eta prime L, which is, this is the identity matrix. All of them are uncorrelated with unit variance. So that's, thank you. That's important, because when you program and you get the transpose wrong, I'll tell you a story about that in a second. But so we got what we need. I wrote a code to do hierarchical bays. Actually, the first version of the code was done by David Revelt, who has worked with me in this area. He's a brilliant person. Fortunately, he had to join the Air Force after graduating. So wasted before homophobes. Nevertheless, the code, we couldn't figure out for months what was going wrong. It wouldn't reproduce what we knew had to be results. And it turned out that we forgot one transpose sign in the middle of a 1,000-line code. So it's very important. So yeah, correct me whenever you see them wrong. Okay, this procedure, it's obvious that it works, but it's important to see why it works, because it has implications when you're doing simulation and trying to figure out why you're getting the estimates you're getting or whatever. So it's really, I want to kind of look at what's actually going on here. So let's suppose we've got a situation where we've got 3 random terms, and what we're going to do is create them as, let's assume 0 mean, just so we don't have to deal with the mean, because that's not the interesting part. The way we would create them is with a lower triangular Chellis matrix, which will take this form. It's lower triangular in that the zeros are on top, and you've got actual numbers down here. In Gauss, when you ask for a Chellis, it'll give you the upper triangular, so you have to transpose it before you use it. But in any case, and then you've got, whoops, your standard normals, 3 independent standard normals. So we can just write this out explicitly. Our epsilon 1 is going to be the top left element of the Chellis matrix times the first random standard normal element. The second one's going to be, I'm sorry, and the third one it's hard drawing these things without a chalkboard. There. So let's verify the properties of this. The variance of the first term is going to be that this element of the Chellis matrix. The variance of the second one is going to be all the elements in the column, in the row, squared. And so similarly for the third one. So it's important to realize that the variance of any one of these terms is determined by all the elements in the corresponding row of the Chellis matrix. The covariance between epsilon 1 and epsilon 2 is determined by this shared factor. Essentially what's happening here is we're taking independent variables and loading them on to the variables that we're wanting. And this first independent normal enters both the first and second of our error terms. And so there's a common factor going into each of these that creates the correlation. So the row totals, in a sense, the squared elements summed up, give you the variance. And then the elements that are the cross elements give you covariance. Okay? And
shouldn't it be S11 and S12?
what did I do? I think this is right. S11 and S12? Is this right or wrong? Over here. 1, 1, 2, 2, 1, 2.
In the covariance. Instead of being S12 squared.
This is S13, S23,
That's right.
S33. And now this one is right.
S11.
This times this. Ah, you're right. Right. Sorry. Okay, but the idea here is that you've got independent terms to start with, and you create correlation by having them load onto the correlated variables appropriately to create the correlation. And the idea is, since there is any Chellis factor for any covariance matrix, that's simply another way of saying there is always some loading pattern that can take independent variables and create correlation by loading them onto the variables you're interested in. So it's the fact that these two become correlated because they both have the first error term entering it. These two become correlated because they have the first one and the second one entering into it. Okay. Okay, so this works when you're trying to draw from a multinomial normal. Okay? And like I said, it only works when you have convenient properties for convolution. Often you'll want to draw from a truncated normal or from a truncated any other distribution. And we can't use this univariate approach because we can't do inverse cumulative on a multivariate distribution. So what do? There is one procedure that you can always apply, has awkward properties as we'll see, but like I said, can always be applied. And that's the accept-reject procedure. I will show you that there's other ways to draw from a truncated other than accept-reject that if you can apply them you'd want to, but you can always do this accept-reject. Okay, so what is the accept-reject idea? Suppose we have a k-dimensional epsilon, and we want to draw from the distribution as long as epsilon's within a certain range. So this is just a multinomial generalization of what we were doing before. This is now a vector of A's and a vector of B's. Okay? How can you do this? Well, there is one obvious and straightforward procedure that anyone could think of. Draw from F. For each draw, determine whether it falls in this range. If it falls in the range, keep it. It's called accept. If it falls out of the range, throw it away. Call it a reject. You do that a lot of times, your accepts become a draw from this truncated distribution. So save accepts. Okay, these accepts are draws from the distribution you want. Okay. So you can always do that. You just draw from the untruncated distribution, see if the draw happens to fall in the truncation range, and keep it if it does. Okay. What's the problems with this? Yes, from a computer perspective, you're wasting time. You're drawing a lot of rejects, or you could be drawing a lot of rejects, and every time you do one, you're not getting anything that you're going to use, so you're wasting time. More importantly, you don't know how to set the computer, you don't know how many draws to take to get some pre-specified number of accepts. If you want to have 1,000 accepts, how many draws are you going to have to take altogether? Well, you don't know. You can calculate the expected value perhaps by knowing what the expectation is or the probability of being in this range is, but then you don't know for sure. What's even more problematic is that for any fixed number of draws that you take, you can get zeros. You can get no accepts. Okay? It could be that every time you take a draw, you got no accept. And in fact, if this range is small enough, as indeed you'll see in many behavioral models, the relevant range is extremely small, then you could draw and draw and draw and draw and still get no accepts. You can think about this as, what if a person has a choice of whether to work or not every month of their lives from when they're 20 to however old they are? Well, the number of options or possible combinations of sequences of working or not working is 2 raised to the 12 months of a year times the age of the person minus 20. So you could get like quite a few possibilities. And you want to see what is the probability of that sequence that that person had actually occurring. That's drawing from a particular truncated range of densities. And yet the probability of being in that space is going to be extremely small. So you can easily end up with no draws in this procedure for any fixed number. Now the way to solve this, or get around this computer problem, is just to loop to where you keep drawing from F until you get a certain number of accepts. And just let the computer just keep going. Of course, you have no idea how long that's going to take, and it could take an extremely long time. And as we've said, it's wasteful. So you can't always apply this, but you have the problem of not knowing how much time it's going to take to get a certain number of accepts. And that's an issue that you'll need to deal with at some point. Now, importance sampling. What if you have a distribution, you can't use any of the other procedures for drawing from it, okay? But you know there's some other distribution that you can easily draw from. Okay? So importance sampling. Suppose you want to draw from F, but you can't. You can't figure out a way to do it. Okay? What you can do instead is find some distribution that you can draw from. Let's call it G. And draw from G instead. Okay? So the procedure is draw from G. Okay? And instead of taking your draws, weight each of the draws. So you weight each of the draws by a certain amount. The ratio of the densities. You can't draw from F, but you can always just calculate what the density is. You can calculate this function even if you can't draw from it. And so you take a draw from G, you weight that draw by the ratio of the densities, whatever your F is that you're wanting to draw from divided by the G that you're actually drawing from. And then the weighted, or the set of weighted draws, are equivalent to draws from F. Okay, so here we're just taking the weighted thing. What does this look like? Remember I said early on that if you're wanting to get the average income in California, that you sample people throughout California, ask them their income, take the average. That's total random sampling. Often, when you're doing that kind of sampling, what you're actually going to do is not just take a pure random sample, but do a stratified sample. So you'll take a different share in San Francisco than you'd take in Los Angeles or in other areas. Or you might break it down into the types of households that you're calling or whatever, and get a different stratified sample. And then weight your sample so that it looks like California. Okay? So whatever sampling procedure you use that's not totally random, you then re-weight the sample so that it looks like a random sample drawn from California. That's what importance sampling is. It's just applied to a density of unobserved factors, but it's the same idea. You just re-weight your observations, the draws, to give you back your original distribution. Now, I want to show how this works, because it's going to come up in a different form when you're actually doing simulation in some settings. And see what's kind of, I think, a deeper way of thinking about this importance sampling. As I said before, what you're always trying to do is calculate this integral. Okay? And suppose you can't draw from F for whatever reasons. You just would normally draw from F, calculate T for each of those draws and average the results, but you can't draw from F. We can transform this by simply multiplying and dividing by G. If you're just multiplying by 1, that's not going to change anything. So let's divide by G and multiply by G. That doesn't change anything. But now it's expressed this integral in a way that's easier for you to deal with. Yeah?
Tape change.
Tape change. So what we've done here is just take our original integral and transform it, and now this becomes the statistic that we're averaging. So another way to look at importance sampling is we've just transformed our statistic and made the corresponding transformation to the density to give us the same thing, and now we're simply taking an average of a different statistic over a different density, transformed, however, in a way that makes our simulation easier. So all we've done is transformed what we're averaging to be an equivalent thing, but easier to simulate. So importance sampling you can think of in either of those two ways, like it's equivalent to taking non-random samples and reweighting to get your population, or as simply a way of transforming your integral to be more convenient from a simulation perspective. Okay, now Gibbs sampling. These two procedures, Gibbs sampling and metropolis-hastings, are things that have only recently started being used in classical econometrics, and yet the power of them is overwhelming. These are the things that I think we learn a lot from Bayesians from. They've gone a long way down this route. They've gone in a different, using them in different ways than a classicist would want to use them perhaps, but they've developed a lot of the useful techniques. So these I really want, to kind of emphasize them. Gibbs sampling. Suppose you have a density that, a multivariate density, and you can't draw from the joint density. It's just extremely hard to draw from it. But you can draw from the conditional densities. If you calculate the conditional density for each random term, conditional on all the other random terms, it's easy to do. This will often be the case because a joint density, if you condition for each individual element, a multivariate density becomes a univariate density. And univariates are relatively easy to deal with. Okay? So it's usually the case that you can draw from conditional densities if you go conditioning down enough. One term conditioned on all the other terms. Okay? That's a univariate density, and you can draw from that. So what if you're in that situation? Let's have k equals 2. Obviously, generalization's extremely easy. It's obvious. So what we have are epsilon 1 and epsilon 2. We have a joint density that cannot be drawn from but we have conditional densities. We can calculate the conditional density, each of them, epsilon 1 conditional on epsilon 2 and epsilon 2 conditional on epsilon 1 can be drawn from. Now, notice that neither of these is a marginal. So the product of these does not equal that. You know, you're not doing this, breaking it down into a conditional and a marginal. These are both conditionals, each one on the other. What the Gibbs procedure says, essentially, I'll state it in simple words, or intuitive words first and then go through the procedure, is that you can start with any draw of one of these terms, epsilon 1, draw then from the conditional distribution for the other one, given that first one, and then use that here and draw from the conditional distribution for the first one, given the second one, and then just keep repeating that process. Eventually that process will converge on draws from your joint distribution. So you've got this iterative process going on. So let me describe it. 1. You start with any epsilon 1, 0. That's our initial value of one of the two error terms, or random terms. Okay. Draw epsilon 2, 0 from the distribution, its own conditional distribution, conditioning on that initial value for the first one. Okay. This we can draw from. We set the value of epsilon 1 equal to its starting value and draw an epsilon 2. And then we draw a new value of epsilon 1 from its conditional distribution using this value of epsilon 2. And then you do it again. Draw epsilon 2, a new value of that, from its conditional distribution, 1, and so on. Okay. This process eventually converges on draws that are equivalent to draws from the joint density. Essentially, from a picture point of view, you've got epsilon 1, epsilon 2. You're wanting to draw from some density that can be represented as contours. They don't need to be centered on 0, but this is a density that rises here, and these are the two dimensions. You start anywhere, or let's do it actually with a truncated. That makes it easier to look at.
The starting value is...
I'm sorry?
The starting value is not...
Starting value is not relevant. That's the thing. The starting value will determine how long it takes to get to where you've converged, but you will always converge. Suppose we want to draw from a truncated distribution that's below this line. Okay. We don't know how to draw from this truncated normal, or this truncated multivariate distribution, but we do know how to draw from truncated univariates. Okay. So let's start with some value of epsilon 1. Say here, epsilon 1, 0. And then we want to draw epsilon 2 from this space here. It's the truncated distribution of epsilon 2 given epsilon 1. How do we do that? We use procedure number 4. Okay? So we start with a value for one of the error terms, use procedure number 4 to draw a value from the univariate truncated distribution for the other error term. Let's say we get this one here. Okay? As soon as we've got that, we now draw from the truncated univariate distribution for the first error term. Okay? And we take a draw, and let's say we got here. And then we take a draw from this univariate truncated, get something, take from that. As you can see, eventually this is just going to be taking draws from this density. No matter where you start, you're going to end up just taking draws from this density down here.
Even at each step of the way, you interject another level of randomness in your new draw. How do you know when you've converged?
How do you know when you've converged? This is the basic problem with both of these procedures. How do you identify convergence? There's no, to put it bluntly, there's no good rule. You examine your data, start seeing whether if you chop it into blocks, you get pretty much the same moments for each block. That's usually the way to go about it. Often you just do enough of them to where you figure it's got to converge by now. You know, a lot of the commercial software has a procedure where they just take 10,000 of these and you use the last 1,000 or something like that. And so they just kind of set it up that you know, just a rule of thumb.
You use a Goodnessoffit test between successive.
You can get more and more sophisticated using Goodnessoffit test to test hypotheses that the subgroups within you look at, say, the last 1,000. You can break it into 250, 250, 250, and then do a hypothesis test that they all have the same moments. You can do that. You can just look at them. That's a paper topic. There's a lot of research on that. You could like summarize what the research indicates and then see if you want to come up with new approaches. The end result is it's difficult. And that is the key problem here. There are conferences on that topic alone. Tell you the truth, I personally subscribe by the school of it's got to converge by now. It's just, you know, in a sense, if your model is so sensitive to whether you're actually taking draws exactly right, that things get screwed up in your empirical analysis, there's probably deeper problems in your model than that. I don't want to be glib about it, but you know, you've got to take these things in perspective.
Ken, what's the issue? It's not just simply an issue of taking enough draws that you cover the entire supported distribution.
Oh, it's just when you're far enough away from your initial to where it's actually operating as random draws through here. You're right, it has nothing to do with how many draws you want to end up with. It's a question of how many iterations you have to do before you start keeping the draws.
So essentially it's when initial conditions no longer matter. That's what you mean by...
Right. It's called the burn-in. You might do 1,000 iterations or 10,000 of burn-in and then start saving the draws as if, you know, because you expect them to be actual draws. Okay, so that's Gibbs sampling. You just draw each one conditional on the other, and you can always reduce this down to univariates. It doesn't have to be reduced to univariates. All it has to be is, you know, one set of errors drawn conditional on the other. So you just do it at whatever level you need to get the answers. Now, metropolis-hastings. This one's very neat. Not very intuitive, but I want to go through the procedure. Yeah.
Well, I was going to say, practically speaking, what would it look like a distribution that could not be drawn from, but it's conditional ones could be drawn from? Would be an example of that.
Where you would have a truncated.
No, but it just would be an example of a distribution which you cannot draw from, but you could draw from the conditional.
Well, a truncated normal. That's the whole basis of probit analysis, is that you've got a normal distribution for your errors, a truncation area, which the errors have to be within that area to get the observed behavior. And you don't know how to draw from that truncated multivariate normal. This is a very, very prominent issue. And, but you can always reduce that multivariate truncated normal to a series of univariate truncated normals and draw from them. So yeah, this is, probit is a great example of this. there's very few multivariate distributions that you can draw from when they're truncated. It's just except with accept reject. You can always do accept reject. But if you don't like the accept reject procedure because you don't know how long it's going to take to get draws, this is another procedure that can be used.
Here also you don't know how long it takes to convert, right?
Yes, here you have the problem of not knowing how long it converges, which you could see as the analogy to accept reject, not knowing how long it's going to take to get some draws, some accepts. Right. There's other reasons for this. When we get into probit analysis, there's going to be a simulator based on accept reject and a simulator based on this Gibbs sampling procedure. And you'll see that this has desirable statistical properties independent of the pulls of the draw. In fact, you can see that this has smoothness properties that we'll be using. Okay, metropolis-hastings. Suppose all else fails. This is not something you want to go into lightly because it is complicated, but the freedom it gives you is just absolutely astonishing. It essentially gives you the freedom not to worry about densities at all, because whatever you end up with, you're going to find some way to simulate it. It might be with this metropolis-hastings. Okay, again, epsilon is k by 1, and we want to draw from this density. So, start out. I'm just going to describe the procedure. Don't try to understand why it works. You won't. I'm going to, we're using this later in the class, I'll describe why it works, but just what the procedure is. So draw an initial value of the vector. You can start anywhere, or let's start. Okay. Second thing is you then create a trial value for the next draw. So we're wanting to get our second draw, and we're going to create a trial for it. And let's call this trial value epsilon tilde. So we don't know whether we want to keep this or not. We're just going to check it out. How do we get this trial? We take our original value and add to it some random term, where that random term is distributed according to some density that we can choose arbitrarily. Well, there needs to be some restrictions on this that I'll describe later, but the idea is you just draw some deviate to add to your original value from some distribution. Nearly always this is taken as a normal, so all you're doing is taking your original value, adding a normal term to it with zero mean, and moving to a new point. Okay? And then you want to see, do I want to keep this new point? So, the first thing you do is compare the density of this new point with the density of the old point. Okay. First, if the density of the new point is greater than that for the old point, that is, it's more likely to be here than here, then you accept this new trial and set your new variable equal to this trial one. So you accept it and keep it. If not, if it's less than, you don't throw it out. This is not accept reject like that. You don't throw it out. What you then do is do a second test. You compare a random draw, or how to put this. Let's say we accept it with probability equal to the ratio of these. Okay, how do we do that? We compare a random draw from a uniform. So we take a draw from a uniform distribution, that's between 0 and 1. We can interpret that as a probability between 0 and 1. If it's less than the ratio of the densities, then accept. If it's more than the ratio of densities, then reject. Okay? If we accept, we set our new value equal to this trial. If we reject, this is important, if we reject, we set our new value equal to the old value. Okay? So we've got our initial value, we go to a new point, decide whether to keep it or not. If we keep it, that becomes our new point. Otherwise, we go back where we started. Okay? Now, we've got our epsilon 1, which is our next draw, and we repeat the process. Take a movement away from that, compare the likelihood function, either accept it or reject it. If we accept it, we move to that new point. If we reject it, we stay where we were. Keep doing this. Eventually, this will converge on a set of draws from the density. From a programming perspective, it's extremely fast. You can do 100,000 draws in no time, because this is a very simple, branching procedure. Okay? And so from a programming perspective, it's extremely easy to do. Understanding why it works is more difficult. And we're going to get into that when we actually use this procedure to justify how it works and what the details of it are. But the point is, it's extremely good, easy to use. The only difficulty is the one we were describing before with Gibbs sampling. How do you know when you converge? And those are general issues. Okay, one last thing on nomenclature, terminology, then we're done. The way I have described the metropolis-hastings algorithm in this fashion is actually more specific than it has to be. The metropolis-hastings algorithm in general is defined more broadly than this. Nevertheless, practically all applications of the metropolis-hastings become this. Okay, so this is the practical way to do it. The general definition is more broad. In fact, the general definition of metropolis-hastings includes Gibbs sampling as a special case. It's a special case in which you always end up accepting the new draw. Okay? So Gibbs sampling is a special case of the general definition of metropolis-hastings. Both of these procedures are called Markov chain Monte Carlo procedures. Okay, MC, MC, or MC squared. You'll see it in the literature as any of those terms. They're called Markov chain because each value depends only on the immediate previous value. They're called Monte Carlo because we're taking draws. So when you read Bayesian literature, they talk about Markov chain Monte Carlo methods. That simply means metropolis-hastings Gibbs. MC, MC, or MC squared. Okay, any questions? Nope. Come back next Monday for more of this if you want.